Our first lesson is going to be a focused review of atomic history. So the concepts and terms that we cover today should sound pretty familiar as we learn about the structure of the atom. More specifically, our essential question that we're trying to answer here is, how did scientists develop the theory of an atomic world? How did they realize that matter, that everything around us, the pen in your hand, the paper that you're writing on, the screen that you're looking at, the air that you're breathing, how is all of this matter made of atoms? What are they made of? And that particular thing that we're calling an atom, what is its exact structure? Now, we could just memorize this in a variety of different ways. I could just tell you that Rutherford discovered the nucleus, blah, blah, blah. But what we really want to focus on is the connection between data and conclusions, because that's the crux of being a scientist. It's the critical thinking, it's the analysis, is what we're really going to focus on over the course of the entire year. If you're given a set of data or a set of observations, what are the conclusions that you can draw from that set of data, and how can you justify and back them up? Because that's exactly what science is. We're going to look at 4 key scientists, okay? John Dalton, J.J. Thomson, Millikan, and Ernest Rutherford, and we're going to look at the key discoveries and their contributions to our understanding of the atomic world today. So, first, a little bit of just basic atomic structure review. We know now that all of matter is made of atoms. Okay? And atoms have 3 subatomic particles. Inside the nucleus, the center here, the nucleus, are 2 subatomic particles, the proton and the neutron. You should hopefully remember from AP Chem that the proton has a positive charge, and we said it had a mass of 1 AMU. Its exact mass in grams is listed here, 1.67 times 10 to the negative 24th. But when we're comparing it to the mass of an electron and a neutron, which is more often, we can just refer to the mass of a proton as 1 mass of a neutron, as you can also see is also 1 AMU. The difference with a neutron, it is neutrally charged. It has no charge. But the electron, on the other hand, okay, is negatively charged. And the electron has a charge listed here of 9.1 times 10 to the negative 28. 28. Okay? Now, if you remember from AP Chem, we said the electron had a mass of 0. 0 AMU. Well, now I'm saying it's 9 times 10 to the negative 28. Well, let's just think about these numbers for a minute. The mass of the proton and the neutron, okay, is about 1.6 times 10 to the negative 24th. Okay? The mass of the electron is something times 10 to the negative 28. So this number, the mass of the electron, is much, much, much smaller than the mass of the proton and the neutron. A difference of 10 to the 4, which, if we wrote as a number, is 1 with 4 zeros. It's about 10,000 times smaller in mass, or lighter, than that of a proton or a neutron. So therefore, since it's so light compared to a proton or a neutron, that's why we say the mass of an electron is 0. It's not actually that it weighs nothing. It does weigh something. It has some mass, which we're going to talk about in a little bit. But when we compare it to the mass of a proton neutron, it's so small that we can say it's relatively 0. Okay? That's why you can see these values here. The mass in AMU, 1, 1, and about 0. Just good background information to know. This is more of the priority, just remembering these. Electrons, if we remember, are located in orbitals. These rings that go around the nucleus. We'll get way more into depth this year about the structure of these exact orbitals. But what we should know by now and should remember is that every single atom, whether it's an atom of copper, carbon, oxygen, nitrogen, has a nucleus that is filled with neutrons, neutrally charged, and protons positively charged, and electrons that orbit them that have a negative charge floating around the outside. Okay? This is what we know, But where did this come from? This is something that took many, many years for us to realize, and we're only still understanding it more thoroughly today. Well, the first theory of the atomic world was proposed by John Dalton way, way back over 200 years ago in about 1803. Okay, John Dalton took a lot of information at the time, understanding of elements, understanding of compounds, of masses of elements, how they combine to form different compounds, and he developed atomic theory. Okay? And atomic theory was something that unified all of the existing evidence at the time. So, for example, the main component of atomic theory that Dalton proposed was all matter is made of atoms. These discrete particles, these fundamental particles, every piece of matter is made of atoms. And that different compounds follow the law of definite proportions, which is the idea that any compound always has the same ratio of elements in it. So water, H2O, if you have a compound water, it will always have the same ratio of 2 atoms of hydrogen to 1 atom of oxygen, no matter what. No matter where you are in the world, it will have that exact ratio. He also proposed the idea of conservation of mass, which should be very familiar, which is the idea that matter, and energy for that matter, matter cannot be created or destroyed. Matter simply, atoms simply rearrange in chemical reactions. It's not that when a piece of paper burns, that paper disappears. It's gone. But the atoms that were together to make that piece of paper have now rearranged into different compounds and have a different structure than they did before. But the mass of whatever you started with always will equal the mass of what you ended with. So once Dalton had established this tenet that all matter is made of atoms, a lot more research was done into, well, what are these atoms actually made of? And one of the first main experiments was done by a guy named J.J. Thomson back in 1897, where he took cathode ray tubes, which were basically glass tubes like this. They were a vacuum. They had no matter inside. And then a voltage was applied, an electric voltage was applied on one end, okay? And then a beam was passed through. And we didn't exactly know what was in these beams at the time, but that's what J.J. Thomson was trying to figure out. So let me show you what an actual cathode ray tube looked like. Here's a video of a cathode ray tube. I want you to watch the video, and then based on what you see, answer the question that follows.
Pull of the magnet to this beam, and we'll see what it does, and then we'll...
So based on that video, this is a cathode ray tube with the voltage being applied, the beam going across. Based on what you see, answer the question that you see now. What he realized was these particles were negatively charged, since when you applied a negative end of a magnet to them, they bent away. That meant they repelled. Like charges repel, and opposite charges attract. So based on this information, okay, J.J. Thomson was able to deduce that this beam is actually made of electrons. And these electrons must have a negative charge. Okay, so atoms now have some negative charge, but we know that atoms are neutral. So if the overall charge on an atom is neutral, there must be some positive charge in it. Well, how is that positive and negative charge rearranged? Well, what J.J. Thomson proposed, and one of the leading ideas at the time, was something called the plum pudding model. Okay? Plum pudding model. Okay? Which was the idea that here's an atom. We have some positive charge floating around, and we have negative charge floating around inside. And the same number of positives and negatives exist so that the overall charge is neutral. Okay. That was one of the main theories. More scientists contributed more discoveries to figure out, man, is that actually true? One of the next major discoveries and pieces of research that was done by a guy named Millikan in 1909. And he set up a famous oil drop experiment where he took oil in a perfume bottle, he sprayed it into this chamber that had a small little hole. So then because of gravity, these oil droplets fell down through this small little hole. He then could zap them with X-rays to give them some charge. Then there were some electric plates above and below here that he could adjust the electric field on. And when he adjusted the electric field with just the right amount of strength, he could get these oil droplets, instead of falling, to actually just stay right in the middle. Okay, boom, they could just float. And then he could observe them. And he could figure out the exact charge on that droplet because it would be equal to the charge on the plate. That's the only way for the drop to stay floating exactly in the middle. Okay, so Millikan's got these droplets of oil. They're charged because they've been zapped with X-rays. And let's say he gets some data like this. Boom. 3 different droplets. These are their charge in coulombs. A capital C is a unit of charge, a coulomb. Okay. Based on this data that's given, answer the question now. So from that data, we could see if we know the charge to mass ratio, and we know the charge on these droplets, we can also figure out the exact mass of an electron. So now we know that these electrons are in atoms. They have a negative charge based on the cathode ray tube experiment done by J.J. Thomson. Now we also know their exact mass. We're getting more detailed. We're figuring out a lot more about the atom than we did before. Next comes arguably the most important discovery that was made by Ernest Rutherford in 1911. Okay? So if you think about it, John Dalton started back in 1803. We're over 100 years later, but this was still over 100 years ago. The discovery of the atom and its structure is a pretty freaking recent thing. Like I said, J.J. Thomson proposed the plum pudding model, the idea that negative charges, electrons, are floating around in this sea of positive charge. So here's an atom. Blue dots represent negatively charged electrons, positive charge throughout. Rutherford set up the gold foil experiment, which we're going to model in a second and we're going to talk about more thoroughly later. But the goal of the Rutherford's experiment, gold foil, was to try to prove or disprove the plum pudding model. It was the leading theory at the time, but just because so many people believe it doesn't necessarily make it true. So he set up this ingenious experiment to try to figure out, and from the data, which we're going to analyze thoroughly, is this exactly how atoms are structured?